We've been talking about similarity between figures, but sometimes within a figure itself there's some interesting similarity that occurs, particularly with right triangles. Let's talk really quick about what happens when you draw an altitude from the right angle to the hypotenuse. We get the right triangle altitude theorem. This states that the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. When you read just the words, that seems very confusing. So let's look at a picture. Here we have triangle ABC, and you can tell by the box at angle B that it is a right triangle. So if we draw in the altitude BD from the right angle to the hypotenuse, then triangle ABC is similar to triangle ADB. Also, triangle ABC is similar to triangle BDC. And finally, triangle ADB is similar to triangle BDC. So all three triangles created when you draw in the altitude to the hypotenuse are similar. Let's go ahead and prove this theorem.
First of all, I would like to say that angle ABC is a right angle. And the reason for that is this statement right here. So that's given and the definition of right triangle, both of them combined. Next, I would like to say that segment BD is an altitude. And the reason for that is this statement right here. So that's just plain flat out given. But the fact that segment BD is an altitude actually gives us a couple pieces of information that's very handy. And that is that angle ADB and angle BDC are also right angles. And the reason for that is because altitudes have to be perpendicular, so that's the definition of altitude. So we know that we have a couple of right angles up here. Okay. Oh, I am just going to pull all of this right angle stuff together here and say that angle ABC is congruent to angle ADB, which is congruent to angle BDC. And why is that? That's because all right angles are congruent. Remember that theorem? So all three of those angles are congruent. Oh, wait a minute here. I'm noticing that angle A here is in two triangles. It's in triangle ABC, and it's also in triangle ADB. So we can say it's congruent to itself. So angle A is congruent to angle A. But why stop there? Because you will notice that angle C is not only in the big triangle, ACB, but also in the small triangle, BCD. So we might as well say that angle C is congruent to angle C. And of course, what allows us to say that? Nothing more than the reflexive property of congruence. Oh my goodness. I think we can start combining some things here. I see that we have a pair of congruent angles here and a pair of congruent angles here, which is enough to say there are two pairs of similar triangles. Triangle ABC is similar to triangle ADB, and also triangle ABC is similar to triangle BDC. And that is because we have two pairs of congruent angles in both of those triangles. Oh, wait a minute. Notice that angle A here is part of triangle ABC, and angle CBD is part of triangle BDC here. These two angles are corresponding angles in similar triangles. What does that tell us, you ask? That tells us that angle A is congruent to angle CBD. And that is by the definition of congruent polygons. Remember, the definition of congruent polygon says that the corresponding angles must be congruent. Oh, hey, that now is enough to give us another last piece of information. And what's that, you ask? Don't worry, I'll tell you. Notice that we have these right angles here, and we have this other pair of angles here. So now this tells us that triangle ADB is now similar to triangle BDC. And again, this is the angle-angle similarity postulate. So you'll notice that we are now done. We have proven the first part, that triangle ABC is similar to triangle ADB, and triangle ABC is similar to triangle BDC. And then, because of the definition of congruent polygons, we got another pair of congruent angles. So now we can say that triangle ADB is similar to triangle BDC. All done. So with that, let's take a look at the similar triangles in this right triangle. So we have a right triangle here, and we have an altitude here. So our theorem tells us that we have three similar triangles in this figure. And those similar triangles are the main triangle, triangle RCK. And let's pull it out so we can see that a little bit better. Okay, so here's triangle RCK by itself. We also have the medium-sized triangle, which is triangle CYK. So let's pull that out and flip it around so we have a nice alignment here. Triangle CYK. And finally, we have the small triangle, triangle RYC. So once again, let's pull it out and show it a little bit better. Okay, so now that we can see that, we can easily write a similarity statement. And it's a three-part similarity statement. We have the large triangle going across the short leg and then across the long leg, where C is the right angle. That is going to be similar to the medium-sized triangle. So once again, we'll go across the short leg and then the long leg, and Y is the right angle. And then we have the small triangle. So we'll go across the short leg and then the long leg, and again the Y is the right angle. So that is the similarity statement we can write relating the three triangles in this diagram.